Here. So I'd like to welcome everybody to the wire rope termination presentation this afternoon. And hopefully there are some bits and pieces of information throughout the presentation that you will find useful, and hopefully maybe some information that you didn't know in the past. So the one thing that I do want to do, as with most things these days, everything comes with a disclaimer. And I would just like everyone to know that this is not necessarily a scientifically valid test regime that we use to prepare the information for this presentation. The idea was simply to look at a number of termination techniques and get a comparison on a very, I guess, high level basis. So again, it is not necessarily a scientifically valid regime, but it does provide some very interesting information relative to the types of terminations and their performance. So if you have questions throughout the presentation, you can feel free to jump in and ask those questions, or I believe there's a chat function and you can go through the chat function and those questions will get to me as well. So start off with basically just looking at the various termination types that we looked at for this particular presentation. Going through them, we looked at mechanically swaged terminations using multiple compression sleeves or only a single compression sleeve. We looked at both zinc and aluminum. We looked at Flemish I's, Spelter Sockets, U-clamps, fist grips, and various sizes of wedge sockets. Just trying to get a broad spectrum of all the various types of terminations that we do see being used in the field these days. So if you look at these, we were trying to get an idea versus published effectiveness and what we were actually seeing when we did a test of these types of terminations. So typically, if you look at the published effectiveness for mechanical swages, they typically talk about 100%, which means that you are going to see 100% of the catalog strength of the wire rope, even though you have a swedge or a termination on that rope. Same thing for swedged eyes, Flemish eyes, Spelter sockets. All of those claim that you will get 100% of the strength of the wire rope, even though you've added this termination to the rope. If you look at fist grips, U-clamps, and wedge sockets, they typically publish that you only achieve 80% of the strength of the wire rope with those types of terminations. So the setup that we used to test was a very straightforward tensile test machine with fixtures that are designed specifically for testing wire rope. The Crosshead Speed that we used, we tested at 2 different speeds, basically at a 10th kilonewton per second and at 0.35 kilonewtons per second. And we conducted the test pretty much in accordance with the procedures that are specified in ASTM A931, which is a procedure written by ASTM specifically for testing of wire ropes and strands. So the test setup, as you can see there in the insert, it was done where you have approximately 3 to 5 wraps around a drum and then to a anchor that anchors the end of the wire rope. And This is done specifically to try to eliminate any stress risers in the wire rope caused by the fixturing, so that we get pure results in terms of just strictly what the wire rope is capable of doing. In terms of crosshead speed, I talked about the 1/10 of a kilonewton per second and 0.35 kilonewtons per second. And this was done because of the strain rate sensitivity. We looked at a number of different speeds. We looked at the ASTM standard to try to determine the speed at which we wanted to test. We didn't want to basically be introducing a shock load, or we didn't want to introduce significant variation because of strain rate. So as you can see from the graph, if we're down in the 1/10 of a millimeter per second, up to about 0.33 millimeters per second, we stay fairly stable in terms of the strength that we determine for the wire rope. Those speeds are also very consistent with the ASTM methodology. So we conducted our speed or our test at those speeds that would generate about 0.1 or 0.33 millimeters per second. And we felt like that was going to eliminate any variation that we got because of speed of loading. So the wire rope that was used is the standard wire rope that Skyclimber sells and that is used throughout the industry. Basically a 5/16 or an 8 millimeter. The specific rope that we used was a 5x26. It's a preformed extra strength rope or strands and right hand regular lay. It's galvanized and it has a breaking strength of about 10,725 pounds. The country of origin for the specific rope that was used is Thailand, and we used gauge lengths that were either 12 inches, and so that's basically 12 inches of free length of rope, or 24 inches of free length of rope. And as I said, there are multiple wraps around the drum in order to minimize any stress concentrations on the rope. I was actually supposed to introduce that video. I can't talk during the videos because our bandwidth isn't quite enough for discussion as well as videos, and there are a couple of other videos within the presentation. But as you can see from that video, basically we do get failure in the wire rope. I don't know if I can go back to that. Let me take a quick look. I may have to rerun that video. Okay, but as you can see, the rope broke. Although it broke around the entrance to the drum, that was not considered to be due to the wire rope actually going onto the drum. It was just that was determined to be the weakest place in the wire rope, and that's where it failed. So getting more in now to the types of terminations that we looked at. Again, starting in the upper left-hand corner here, we have one mechanically swedged. This is a zinc-coated copper compression sleeve. Going down, we also did this with two swedges, which is relatively common in the industry. where you have 2 swedges with 3 crimps. We also did aluminum. So we have the mechanically swedged with 2 aluminum compression sleeves and 3 crimps on each. We did a mechanically swedged steel compression sleeve. We did fist grips, and we used the standard 3 fist grips that were basically spaced about 3 inches apart, and those were properly torqued. It says here 30 foot-pounds. I think the actual torque that's specified is actually 35 foot-pounds. And just to understand what the impact of properly torquing fist grips would be, we also conducted the test with the fist grips improperly torqued using only 10 foot-pounds of torque on the fasteners on the fist grips. Even though the SAIA and a number of people preclude the use of U-clamps, we did want to take a look at U-clamps and see what kind of performance they provide, and is the fact that we're not supposed to use U-clamps, is that legitimate? And we looked at U-clamps both in terms of properly installed on the wire rope, which is the saddle on the live end, versus incorrectly installed U-clamps, which was putting the saddle of the U-clamp on the bitter end of the wire rope. We looked at 2 different wedge sockets. When I first set out to try to find all of the various types of hardware needed for the terminations, I found it relatively easy to find 3/8-inch wedge sockets. I was also told by a number of people in the industry, yeah, we just use the 3/8 because they work fine, and sometimes we have a hard time finding the 5/16. So I wanted to try the 3/8 to see how they would indeed perform. I also was able to locate some 5/16-inch wedge sockets, so we wanted to compare the difference between properly sized and slightly oversized wedge sockets. We looked at a swedged eye, we looked at Flemish eyes, and we looked at Spelter sockets. And Spelter sockets was something that was a little new to me. I really hadn't seen those during my years in the industry. For those that don't know, a Spelter socket is simply a cone shape that the wire is put into that cone, and then a molten or a liquid material is poured into that, and then the liquid material solidifies and it locks the wire rope into that cone shape in the socket. For our particular test, we used a Spelter socket with epoxy. We didn't use the, I guess, what might be more traditional, which was a zinc material, which would be a molten zinc that would be poured in. The company that we use to prepare these samples for us uses epoxy, so that's what our Spelter socket was built around.
Hey, Mark, we did have one question.
Okay.
It says, before compressing the double swag, is there a specific distance between one another?
The rule of thumb that we use when we prepare those is typically that the 2 swedges, or the 2 compression sleeves actually, the 2 compression sleeves should be spaced approximately 1 rope diameter apart. I think if you look at most literature, it will tell you that for our size wire rope that we were looking at, which is the 5/16 or 8 millimeter, most of the compression sleeve manufacturers only specify that you need a single compression sleeve. So the fact that you may use 2, I don't know that there is a hard and fast rule that says exactly how far those should be spaced apart. So as I said, we use the rule of thumb of one rope diameter, and that's what was used in the preparation of the samples for these tests that were conducted. Okay, so if we get into actually looking at the test results that we started seeing, if we look first, as I said, mechanically swedged with one zinc-coated copper compression sleeve, and then multiple crimps on that compression sleeve. So if you look at this, we come up with, if you look at our charts, these are in kilonewtons and in extension in millimeters. So if you want to convert kilonewtons to pound-feet, you basically do that by multiplying by roughly 225. So in order to convert our millimeters to inches, you're dividing by 25.4, or a rough approximation is just dividing by 25. So for our first one, you see that we got about 11,000 pounds of force that it took to break the rope, and we had about 1.5 inches of extension. And on this particular one, under the observations, you can see there that the failure occurred in the wire rope, not in the termination. Although it is very common with the mechanically swaged terminations that the failure, although it occurs in the wire rope, it often occurs just below the mechanically swedged compression sleeve. So there may be a slight stress riser phenomenon going on there. But again, the failures are typically in the wire rope itself. So, and as you recall, or you should recall, I said that the wire rope that we were using had a catalog breaking strength of about 10,750 pounds or 725 pounds. So in this case, we actually got a failure that was higher than the catalog breaking strength of the rope. So if we go to basically the same approach, only with the two zinc-coated copper compression sleeves, again, the failure occurred in the wire rope just below the lower compression sleeve. And in this particular test, you can see the result that we actually got in terms in the inset picture there. Where you can see that there were a couple of strands that were not failed, but the majority of the strands all failed. And again, the breaking strength is right in that exact same region of about 11,000 pounds of force. Our extension, again, pretty close to about 1.5 inches. So when we go to the aluminum, we see very similar results to that we see with the copper-coated sleeves. And again, the extension is slightly more than what you get with the, or what we saw with the copper compression sleeves, but not much more, about 1/4 inch more extension. So we will talk a little more about aluminum sleeves because there are some recommendations by manufacturers of aluminum sleeves that even though we get performance that is acceptable, they may not be acceptable for use in lifting applications. So looking at mechanically swaged type fasteners still, but looking at a steel compression sleeve rather than copper or aluminum, you can see again in the inset picture where the failure occurred, which was in the wire rope, again, just below the swedge. And on this one, all strands failed. It was a complete separation of the wire rope from the termination. Braking force a little bit less than what we had seen in the previous mechanically swedged types of terminations, and the extension or the elongation roughly the same, right between what we saw with the copper and with the aluminum. If we go to our fist grips that are properly torqued, and again, it shows 30 foot-pounds here. I believe the proper torque is actually 35, and that's what was actually used. I just had an error in my presentation. So, but this was set up with 3 fist grips, which is what is recommended, and spacing them roughly 3 inches, or for a lot of people, they just use kind of the width of their hand as to how far apart the fist grips should be spaced. Again, our failure occurred in the wire rope just below the lowest fist grip that was installed. So the braking force right in the same range as our mechanical swedges, up around 10,800 pounds, and the elongation was more along the lines of the aluminum, where it got a little bit longer in terms of elongation than what we saw with some of the other ones. And when we go and we compare that to improperly torqued fist grips, which these were torqued to only 10 foot-pounds, what you can see is that our elongation increased dramatically. The thimble actually showed severe deformation, and our braking force was also significantly less than what it was when we have fist grips that are properly torqued. So, and you can see in terms of the elongation, we're clear out to almost 60 millimeters. So we're where we were at maybe 1.5 inches. Now we're out, you know, up against 2 inches, maybe 2¼ inches of elongation. So the big question that I would ask to everybody is, when you have your technicians in the field that are installing fist grips, do they have a way of monitoring the torque when they install those fist grips? Because the proper torque on the fist grips is something that is very important to proper performance of those fist grips. As I said, we wanted to look at U-clamps and just see, you know, how do U-clamps actually perform? And if you look at this with 2 U-clamps properly installed, they actually don't perform much worse than some of the other techniques. The braking force was clear up around the same braking force, being close to the 11,000 mark. And the failure occurred in the vicinity of the lower U-clamp. Although one thing that, you know, in the observations that you see on this slide, it does note that the failure can occur directly under the U-clamp. And we'll see some other pictures a little later on in the presentation that help to explain why that may be. Also with the U-clamps, you do see more elongation or more extension. So there likely is some sliding of the wire rope between those clamps. If we look at incorrectly installed U-clamps, and this is the saddle on the bitter end rather than on the live end of the rope, you can see that the failure occurred actually between the 2 U-clamps. And our force to fail was significantly less than what we'd seen in the other instances. The elongation wasn't as high, but the failure did occur between the 2 of them and at a significantly lower load. Looking at a mechanically swedged eye, again, we're back to failure occurred in the wire rope, not in the termination, back to that 50,000 kilonewton range, or the 11,000 pounds of force. This one, the elongation was slightly less, probably a 1/4 inch less than what we've seen in some of the other ones. The Spelter socket, again, performed very similarly to the mechanical swedges and many of the others that we had seen, with about 11,000 breaking force and the elongation in the 1.5-inch range. The wedge socket, if we looked at the one that a lot of people said, oh, you know, we can't find 5/16 as readily, so we'll use just a slightly oversized and use a 3/8-inch wedge socket. What we saw with this was that there was significant slippage within the wire rope through that wedge socket before it actually bound up and then allowed the wire rope to fail. And in fact, in this, we never actually failed the wire rope. We actually pulled it free from the termination. So, and that was after about 2 inches of elongation. So we'll see some more on the test results with the 3/8-inch wedge socket a little later in the presentation. 5/16-inch wedge socket. So if we look at the socket that is properly sized for the type of wire rope that we're using, the breaking force is a little lower than what we have seen with some of the other termination types, and the elongation is significantly higher, and that's attributed to the fact that the way the wedge socket works, you truly have to drive the wedge into the socket. So that allows some slippage in the wire rope, as well as some elongation because of the fact that the wedge has to drive into the housing, and that allows more elongation or more extension. Okay, looking at the Flemish I, and for those of you that may not be familiar, and there may be some different definitions for a Flemish I depending on I guess just the individual and what they call these, but this is basically the Flemish I as our supplier provides them. They actually weave the wire rope back into itself after going around the thimble, and then they put a steel compression sleeve over top of that. And so you get the interweaving of the strands of the wire rope as well as the steel compression sleeve. And in looking at this, we get a little more elongation than what we had seen on some of the other terminations, but the force is very similar, and the failure once again occurred in the wire rope and not in the termination itself. So if we kind of summarize all of the results just in terms of breaking load, what we see is that the Flemish I, the socketed or the Spelter socket, the swedged end fitting, going down the 2 aluminum compression sleeves, the 2 copper compression sleeves, and just marginally 1 copper compression sleeve. All of those basically come up to the strength of, or the catalog strength of the wire rope itself. So that being at the 10,725 pounds. So all of those would be equally adequate methods of terminating wire rope. Some of the things that stand out for us, however, that are, I guess, would be rather alarming would be looking at the 3/8" wedge socket and seeing how it performed, looking at U-clamps installed backwards, even though a U-clamp installed correctly performs reasonably well when they're installed backwards, significantly less than what the value of the, or the catalog value of the wire rope is, and even getting down to where they're almost below even 80% of that. Fist grips that are improperly torqued, you can see that having the proper torque on your fist grips is vitally important to those properly performing. They are published as having 80% of the strength of the wire rope, and they perform significantly better than that in our testing. So looking specifically at some of these that did not perform as well as we might like, looking at the U saddles or the U clamps, there was visible distortion in the wire rope even before we applied any load to the rope whatsoever. So you can see between the two clamps, before any load has been put on that, you can see that the wire rope is already starting to show some distortion. And if we look at the wire rope both before and after, if we just take the clamps off before we've put any load on it, you can see the deformation that has occurred in the wire rope. And then after the test, you can see how that deformation has been exaggerated in the wire rope. So the one thing, if you were to ever use U-clamps, it is absolutely apparent that you would never be able to reuse that wire rope again because of the damage that has been done to the wire rope simply by installing those clamps. And then when you compound that with the poor performance of the U-clamps when you install them incorrectly, which can very easily be done, you can understand why in our industry U-clamps are not permitted to be used. So, and you can see here again, the U-clamps, because of the damage done to the wire rope, you can see that we do actually fail the wire rope right under the U-clamp, and we really have to attribute that to the fact that we are damaging that wire rope before we do anything. Just simply by installing those U-clamps, you've done damage. Okay, in looking at fist grips, which are commonly used, if they are not properly torqued, they can be problematic in the field as well. So once again, we have another video here, and as I said, I can't talk through the video because of the fact that the bandwidth just isn't sufficient. So I'm going to play the video now and let you see exactly what happens when you load up wire ropes with fist grips that are improperly torqued. Okay, and you can see, and after this particular test was conducted, you can see how much deformation that we got in the thimble. And you can see from where that red mark was placed on the wire rope at the lower fist grip, you can see how much that moved throughout the course of the test. So even though we do get failure in the wire rope, you can see that you are definitely moving the wire rope through those fist grips. So again, I have to ask the question, when you go to the field and install fist grips, are you assured that you are achieving the 35 foot-pounds of torque that are required on the nuts on those fist grips, so that you know that the wire rope is not going to be slipping through? One of the things that has been recommended to me is that there are special adapters that can be used with a standard socket. It doesn't have to be a torque wrench, but these are special torque adapters that can be preset to a specific torque, and then they will click much like a torque wrench. And these can be used with standard types of ratchets and sockets. And that might be a piece of equipment that you would want every technician or every mechanic to have in the field when they are installing fist grips, so that they know specifically that they had achieved the 35 foot-pounds of torque that are required for fist grips to perform adequately. Okay, going on and looking again, this is going to be another video. And again, this is the 3/8 inch wedge clamp. And if nothing else, this reinforces for us that we shouldn't be using equipment that is not properly sized for a specific application. So I'll start the video and it kind of speaks for itself. So with the 3/8 inch wedge clamp, we did experience significant rope slippage prior to the rope failure. And then after the rope failure, as you saw in the video, the entire wedge became dislodged from its fitting. And in looking at the wedge after the test, you can see the damage to the wedge itself by the rope sliding through it under pressure as it was. So for anyone that may be using a 3/8 inch wedge clamp, I understand that these are significantly higher loads than what you would ever experience in the field under normal operations. But there is a possibility under abnormal operations that significantly higher loads can be generated by hoist on the wire rope. And we would never want to get into a situation where we actually pull through the wedge through that its housing because of the fact that we're using an oversized wedge clamp. So in looking at aluminum compression sleeves, the performance of the aluminum sleeves in our tests showed that they perform as well as copper compression sleeves, and equally as well as a number of the other termination types that we've looked at. But what it doesn't take into account is some of the other issues associated with aluminum as a raw material. And if you look at some of the literature that is published, what you will find is that the fracture toughness of aluminum compared to copper is significantly lower. You will also find that the energy absorption capacity of aluminum is also significantly less than copper. In addition, the coefficient of thermal expansion of aluminum is significantly higher than copper, which would allow more what we'll refer to as movement of the aluminum compression sleeves relative to the steel wire rope, significantly more movement during temperature changes than what you would experience with copper. So although the tensile strengths are similar and therefore the performance as a termination are similar, the long-term performance of aluminum gets called into question because of the fracture toughness and its ability to absorb energy. And I think that many of the manufacturers have therefore recommended that aluminum compression sleeves not be used for lifting applications. And I think they would double reinforce that and say we would never want to see it used in a lifting application, which is a man-rated lifting application, because of these deficiencies in the raw material versus the other raw materials that could be used that are more suited to lifting and man rating. So our conclusions after looking at all these different types of terminations. Number one is that what we found is that there are many effective types of terminations when they are properly implemented. So from this, again, my disclaimer at the beginning, this was not a scientific study, but from this limited evaluation that we did, what types of terminations did we see that worked extremely well? Well, swedged with 2 copper compression sleeves, a Flemish I, done as I described earlier with the back weaving and 1 steel compression sleeve, the Wedge Socket, and the Spelter Socket with an epoxy wedge. All those worked extremely well and provided strengths that were greater than the catalog strength of the wire rope. What types performed adequately? Well, the swedged with a single copper compression sleeve, the swedged with 1 steel compression sleeve, and 3 fist grips, and the 5/16" wedge socket. Again, with fist grips, we always have to put the disclaimer in there if they're properly installed, because as you saw in the video, improperly installed fist grips can be problematic. So from our evaluation, what types of terminations perform poorly? Well, fist grips, when improperly installed, do not do well. U-clamps, because of the damage that they do to the wire rope itself, even unloaded, we can understand why they perform poorly and why they should never be used in the types of applications that we're talking about here. And again, the 3/8" wedge socket, termination hardware needs to be properly sized for the wire rope that's being used. And then finally, our one exception is aluminum compression sleeves performed well, but they should you should follow the recommendations of your manufacturer on whether they are approved for man-rated lifting applications. And I always like to finish up the presentation by just talking about a little bit about wire rope. We've talked here extensively about terminations for wire rope, but we also have to remember that wire rope is a consumable. You know, it begins to deteriorate upon first use. So it is essential that every time that you know, you are getting ready to use a wire rope, you must have an inspection that's performed by a competent person. And you know, that inspection should be done at the start of each work shift and after any occurrence that could have an effect on the wire rope's integrity. And you do need to inspect the entire length of the wire rope when you do these inspections. And you know, just to reiterate, and looking at you know, what OSHA says you have to look for when you're doing an inspection on wire rope, you know, any physical damage of the wire rope that might impair its function or strength, you know, kinks in the wire rope, 6 randomly distributed wires broken in one rope lay, or 3 broken wires in one strand. I know a lot of people have a significantly tighter criteria than that, but that is the minimum from OSHA. The loss of, what OSHA says is the loss of more than 1/3 of the original diameter of the outside wires. That's pretty tough to measure. I'm not exactly sure how somebody in the field would measure that. So I think probably the proper approach here is to use a preset reduction in the original diameter. We specify a 5% reduction in the original diameter, that is when the wire rope should be replaced. You know, any heat damage on the wire rope is definitely a cause for taking that rope out of service. Any damage caused by improper grounding when you're welding, again, that's one that is an automatic that the rope needs to be taken out of service. And then any evidence that the secondary brake on a traction hoist has activated during an actual overspeed condition and it's engaged on the wire rope, that is another instance when the rope should be taken out of service. And again, this is minimum criteria established by OSHA, and you may want to establish more stringent criteria as you feel is appropriate to assure that the wire ropes that are being used by your associates or others in the field are going to be adequate for the operation that needs to be performed. So with that, I'll open it up to questions that anyone might have relative to the information presented.
Hey, Mark, I do have a question, so I'll get things started. If a copper compression sleeve is improperly swagged, can that cause milking further down the wire rope?
I'm not sure that the improper swaging of a compression sleeve would cause milking further down the wire rope. And again, I'm not an expert in wire rope by any stretch of the imagination. I'm just going by the limited experience that I have. But milking, in my experience, is caused more by the rope manufacturing and potentially some unequal tension in the strands of the rope. And that should not, unless you're doing something to affect the wire rope further down while you're doing the mechanical swaging, that should not lead to any type of milking. Again, my experience has been that that's been more from manufacturing the rope, and we are actually able to create milking just in a wire rope that has had nothing but an end or both ends of the wire rope bolted.
And I actually have another one that came through on the chat. This one says, when using a single sleeve, doesn't the manufacturer recommend 4 presses?
And you would have to go by the particular manufacturer, but the number of presses is typically associated with the diameter of the rope that you're using. I've seen literature that goes from 1 crimp, 2 crimp, 3 crimp, 4 crimp, all the way up to 5 crimps, depending on the diameter of the particular rope. So you would have to go to the manufacturer of the sleeve, of the crimper that you're using, and the diameter of the wire rope to ascertain exactly how many crimps are required. Okay, and somebody has just weighed in, and I was informed that I said that the proper torque for fish grips was 35 foot-pounds, and I've been told that it is indeed 30 foot-pounds. So, I correct myself. It is 30 foot-pounds for standard fish grips that are used in the industry.
And I just wanted to note that if anyone else does have questions, you're more than welcome to unmute and ask, or you can send it over in the chat and I would be more than happy to relay them to Mark to answer.
Okay, if there aren't additional questions, I would just like to express my thanks to SAIA for giving me the opportunity to present this information to you. And if anyone has any questions, you can feel free to reach out to SAIA, or my contact information should be on the screen there. You can feel free to reach out to me directly. But I thank you for your time, and I thank SAIA for the opportunity to present this information.
Hey, Mark, this is Harold. I am one of the chairs of the Suspended Scaffold Council. I wanted to personally thank you for this outstanding information. I do believe you offered this on sticks, or available to people that attended your live presentation when we did this at the last conference. I'm not too sure you still want to make that alive or not, but this information is fabulous. Once again, anybody in the suspended scaffold industry is I'm sure, impressed with what we discovered and just the information. The fish grip part, yeah, it's 30 foot-pounds, and the U-bolt, the reason the U-bolts weren't used is people didn't know which way to put them on, and they didn't perform very well when you put them on backwards, but they always crushed the rope, which left that rope damaged for the next use. So one of the reasons OSHA doesn't like them and none of us do is mainly because they were not known. It was an improper way to put them on, and also their damage that they did. But thank you, and once again, thanks to the SAIA for representing this program.
And Harold, I will say that the offer that we made at the presentation in September stands as well. Anybody that would want a copy of the presentation, we are more than happy to provide that information. You can just go through SAIA and they can get the information to us, and we will distribute the, I think it's a slightly abbreviated version. There are no, are the videos in there? The videos aren't in the presentation that we send out, are they? But we will provide the information to anybody that would request it.
Is that only for members?
We will have this video posted in the members only section of the SAIA website. If you would like to, if you're not a member and you would like to view it, just, shoot me an email. You should have received my contact information on the confirmation, or you can get a hold of Mark here, and between the two of us, we'll get you taken care of.
Thank you.
And hey, Mark, I did have one more question come in. Do you have a moment for it? Or do you want to
Yeah,
handle
sure.
it offline?
Nope, I've got time.
Okay. It says for the inspection page, does it mean when the wire reduced by 5% that you have to replace the wires? There seems like a huge jump between a third in the code to the 5%.
Well, if you look at what the code actually says, it's very difficult to measure specifically what the code says, because the code says the loss of more than 1/3 of the original diameter of the outside wires. So that is almost impossible to measure. So when we look at the 5%, we're talking about the overall diameter of the wire rope. So if you start with an 8 mm wire rope and you take 5% of that, it is 4/10. And so that says that wire rope has dropped down to 7.6 millimeters in diameter. That is something that using a special set of calipers for measuring wire rope is very easily measured, and is something that I think most people can sign up for. So OSHA is not saying that you can reduce the diameter by 1/3, and we're saying 5%. OSHA has this kind of convoluted, a third of the diameter of the outside wires. We're saying 5% of the overall diameter. So, hopefully that clears that up.
Sorry, I was on mute. I have another question for you, Mark.
Okay.
How do these connection types vary in effectiveness if the wire rope are stainless steel? Would be in horizontal lifelines versus galvanized wire rope, if at all?
We have not done any evaluation of these termination types using stainless steel wire rope. I do have experience, however, doing terminations with wire ropes, and with absolutely no scientific experimentation to back it up, I would say that the terminations would perform similarly on a stainless steel wire rope as they would on the wire rope that we tested, which was a steel galvanized wire rope. The biggest difference is going to be that the stainless steel wire ropes typically are much lower in strength on their own. So of course, your overall performance is going to be lower, but I think the terminations are going to perform similarly on stainless steel rope as they do on the galvanized steel rope.
Okay, Jackie, anything else?
I do not believe so.
All right, Mark, thank you very much. I also want to thank Sky Climber LLC for sponsoring this. And want to remind everybody that registration for the SAIA annual convention is open. We will be in Phoenix from September 14th through the 17th. So be sure and go register. With that, we will end this webinar.